Good morning. It's not a big group, we all know each other, but welcome to the conference. Thank you for organizing it and thank you for joining it. And of course, as always, it's nice to have some partners, sponsors that do enable the event. We all know each other, so I don't think I need much presentation. I planned to talk first half an hour about me, but now I will skip this. No. Anyway, I have to be a little bit faster since we need to stop on time, I guess. So the next presentation can start in time. So what I will be talking about is this association rules algorithm and show implementations in different languages and products and comment them. And I will actually develop this algorithm step by step using Transact SQL and then show also how it works in R, how it works in Python. Even we have custom visualizations in Power BI and analysis services, multidimensional data mining also has a nice implementation of this algorithm. So first, brief introduction. What is this algorithm about? We have transactions which are defined by, let's say, order number, something that was purchased, set of articles or items that were purchased in a single transaction, in a single visit of a customer to our website, or in a single visit of our customer to our retail store. And this set of items or item set is a combination of items in a single transaction. Now we can search for item sets that consist of different numbers of items. One, basically this is not really an item set, but still item set with a single product, or we can search normally for item sets with two products. We can search even for item sets with 3 or 4 products and more. Typically, we are interested in combinations of pairs or item sets that consist of 2 products. Now, we are searching for those that tend to appear together in many transactions, so pairs that usually are purchased together. Immediately, let me start with also the problems with this algorithm. It's not actually the problem of the algorithm, it's the problem of general problem. Is that how do you find those item sets of interest? The general problem is that you can have enormous number of these item sets. Imagine a chain, a retail store chain, they might have like 1 million different products. So basically any combination of 2 products can be an item set. So like you can start with cross join of all possible combinations, million by million, right? So it's billion of billions possible combinations. Of course, you are interested in those that appear very, very frequently. We can, let's say, make an overview of the results. We cannot read, I don't know, billion of combinations. We can read maybe 100 combinations in a reasonable time and also find some value in them. So typically we start by checking those that are the most frequent, but also it's worth mentioning that we should also check negative associations. So one product in basket means less probability for another one. The problem here is that we are searching for something we don't know, and the most frequent item sets are usually something that we would expect. Of course, we are also going personally to retail stores and you know what kind of things you are typically purchasing together. So many times these most frequent item sets don't tell you much, because you already expected them. So you want to find those that are not expected. Now, after this initial introduction, let's go and start developing the algorithm. First thing we can define is support. So it's number of transactions with item set compared to the total number of transactions. Here I have 5 transactions, and we have cola and frozen pizza in 2 out of 5 transactions. We can express support as an absolute number, or even better, as a probability. So we have probability 0.4 for this item set in whole sets of transactions. But item set is not directed. If you look at the rule on the slide, if customers purchase cola, then they will purchase frozen pizza. This already has somehow a direction. So cola is the condition and frozen pizza is the consequence. Now we could also turn this rule around and say if customers purchase frozen pizza, then they will purchase cola. So which rule is better? We wanted to get the rules, not just item sets. So which rule is better? Is there somehow that we could define this direction of these rules? Now, if we look at these transactions, again, in transaction 2, we have a combination or item set milk, potato, chips. Now, potato chips appears in this transaction only, while milk appears also in transaction 1 and transaction 4. So let's check this as rules. Let's try to express this item set as rules. If potato chips, then milk is valid whenever is potato chips there, milk is also there. The opposite rule, if milk then potato chips, is valid only in 1/3 of cases. Milk is in 3 transactions and only once it is associated with potato chips. So apparently this rule, if customers purchase potato chips, then they will purchase milk, is somehow a rule that we could be more confident in it. And we can define the next measure, which is called the confidence. So this is the support for the combination divided by the support for the condition. Combination, in this case, potato chips and milk, is 0.2. It appears in 1 out of 5 transactions. And support for milk is 0.6 or 60% because it is in 3 out of 5 transactions. But support for potato chips is also 0.2. So we have confidence of 0.33 for the rule if customers purchase milk, they will purchase potato chips, and confidence 1 for the opposite rule, if customers purchase potato chips, they will also purchase milk. So somehow we found the direction of these rules. Let me start with DMOS. So I will start with Transact SQL because it's the simplest way to develop this step by step. Right, in R, we already have functions that do everything for us, so we cannot see what is happening inside the function. First, I have in AdventureWorks DW 2 views, and I will just create tables for better performance. So I will materialize the data and add primary keys. So let's see. First one is ASOC line items. It was a view, now it's a table. So I have order number, which defines the transaction. And then we have model. So this is tripped in these first transactions, 3 products were purchased. Row 350W, cycling cap sport 100. And I also have a line number. This is done from internet sales. So sometimes we can even define order of items in an item set. In a retail store, order of items is not defined because, of course, when you come to the cashier, the order is completely mixed compared to the one as it was when you put the items in your basket. So, but in internet sales, we can even define the order of items in an item set. So apparently in this order, row 350W, whatever this model is, was purchased the first, and then cycling cap, and then sport 100. Basically, for basic association rules, this is all I need. And I could start analyzing, but I have also orders in a separate table. Why? Because I have linked to customers, so I could add some, let's say, demographic data from customers, and this helps me maybe analyzing data in groups. So let's start analyzing. We can start with the simplest query, frequencies of item sets with a single model. This is basically just count of the models in these line items. So apparently the most purchased product is Sport 100, then water bottle, patch kit, and so on. So water bottle is pretty popular. Now I will go to negative part first. So I will try to find which models have been purchased only once in a single order. So it means customers came to our website, purchased this model, and never returned and never purchased anything else. These are, let's say, define them as really negative models. So I am joining these tables to get also possibility to group over customer key, and I'm searching for those that have a single order and a single model in this order. So these are customers that have one purchase with a single group by customer ID, so one model in a single order with a single item. And now I can count this over models in an outer query, order by count descending, and I see like maybe the most negative product is water bottle. Now, if you remember, this was also the second mostly sold product. So this already shows you the issues with association rules. You should be very careful with interpretation. Of course, if people many times purchase water bottle, there will be also some people that will purchase only this and nothing else. Also, it makes sense that you make this in real life context out of just checking the results. It sounds pretty logical to me that water bottle is many times purchased alone. Imagine that you went for a biking trip. You want to bike, let's say 100 kilometers, and then you realize you forgot to take water with you. This is something that is then, especially in the summer, impossible to ride for 100 kilometers. So you stop in the first store, purchase quickly water bottle, fill it with water, and continue with the trip. And we see like this first result is not really useful. So maybe this woman's mountain shorts is more important as a negative product. You see, this is how you start to gain insights in your data. Now, since we have this in our order, since we have this demographic data like region, income group, we can also start analyzing this by other columns. For example, I will also pivot this by region and see the results. I see especially NAM is short for North America, water bottle, and also women's mountain shorts are very negative, especially in North America. Road 750 is approximately the same, has approximately the same negativity in all regions. And I could also try with income group and check. And I see that income group is not so important, but it is for maybe more for women's mountain shorts, low income group. This is not so negative product in low income group. So probably income group tells me more than region. Now I will stop analyzing in groups. This is just the expulsion of all other further queries. If you wish, you can always add analysis in groups. So since I will not do analysis in groups anymore, I will do all analysis from line items table only. Now I'm searching for item sets with two models, and I'm joining line items to themselves, joining on equal join on order number, and where model 1 is, let's say, alphabetically greater than model 2. So these are item sets with two models. So this is the most popular combination, water bottle, mountain bottle page. The second most popular is water bottle, road bottle page. Again, if you look what we know about, let's remind ourselves what we know about water bottle so far. It was second most frequently sold product. It was also first most negative product. But now we see it really goes well together with other products. So apparently that result that water bottle is a negative product is not important. We can simply disregard it and treat water bottle as a positive product. You see, this is an example that you have to view this data on from many different angles. Then you can get the whole idea what is important and what raises the sales and what lowers it. Now I will express the same query instead of with the join. I will express it with apply and get completely the same result. Now, which one would you prefer to use, join or apply? In this case, I would definitely go with apply because I think queries are a little bit more readable. But you know, let's say from performance perspective, join SQL Server has more possibilities than with apply. With apply, SQL Server will always use nested loops, which in this case makes no difference. Nested loops is the best algorithm in this case. When it would matter if you would have, this would be much bigger problem, if you would have few orders only, and then maybe, I don't know, 10,000 items on each order. In this case, this would be a bigger problem anyway. Let's go for a second in this query. So basically, this is non-equal condition based on a single order number. More or less, this means half of cross join. But since we have like 5 line items in an average order, it's not a big deal. But if you imagine that if you would have thousands of different line items, then here you would maybe get for a single order, 1 billion rows in the result. And this could be a problem, which could be somehow mitigated by using join, and then SQL Server would go to hash join instead of nested loops, but still it would be extremely slow. This is a general problem. You cannot do much about it. You cannot do much. What if you come to such situation? Well, you have simply to lower the number of combinations. You can do this by using groups of products, like you can use product taxonomy, like product subcategory, product category, and first you try combinations of different categories. Then when you find 2 categories that go well together, you expand one to subcategories and then second to subcategories and so on. Because basically this is logical problem. You cannot optimize it much if you have a cross join of million by million rows. Now with apply, it's also easy to add. Now I have first result with 2 models. Now I can add another apply from the results to the same line items and add the 3rd model. And I could continue with adding 4th model. So let's check the item sets with 3 models. So the most popular is mountain bottle cage, mountain 200, water bottle. Of course, the support goes down. the more items I have in an item set. Now I will just go back to two models and try to express item sets as a rules. Now I want to get both combinations where model from the left is lower alphabetically than model from the right, and the opposite combination. So I have changed the condition here. I have changed the condition. Still I'm joining over order number, but now model from the left must be different from model from the right. And now I can count the support for these item sets. I'm still expressing item sets only, so we have two rows for combination water bottle, mountain bottle cage, and mountain bottle cage, water bottle. Of course, the support is the same for both rows. Now let me add the rules. Besides the support for the combination, I need also support for the condition. Condition is simply count of a single item. So I have to calculate the support for condition, and I will also calculate this as a relative number. So I need count of distinct transactions, right? I will also calculate percentage, support, and confidence as a relative number. And I need also the number, so I need also the number of orders. So I'm counting distinct number of orders counting distinct, counting distinct number of models on all orders. And I also need the total count for a relative number, which I simply add with a cross join of a single row. Total count is just total count of orders, 13,000. Now I'm ordering by support and confidence, and I calculate confidence in outer query. So I have confidence, which is support, right? Which is simply absolute number, and model count as confidence. So count of single item. And let's see how this works. And you see query becomes a little bit more complex. And now I have first item set, the most popular, mountain bottle cage and water bottle. We still have both combinations. We have support as an absolute number. We have support as a relative number. So this is 7.63% of all transactions. But look at the confidence. We found kind of internal order. So confidence for the first rule is 83%. Confidence for the second is only 40%. So apparently rule if mountain bottle cage then water bottle is better than the rule if water bottle then mountain bottle cage. Okay, we already know some things, but there are some other measures that we could define. Lift or importance of an item set is defined as probability for the combination for the item set divided by the probability of item A multiplied by the probability of item B. So combination, if this multiplication of probabilities is completely equal to the probability of combination, means that I have no specific impact of one product on another. So if importance equals 1, then it simply means that these are two independent items. If it's greater than 1, then two products are positively correlated. If it's lower, then they are negatively correlated. But also the bigger the lift or importance is, the stronger this correlation is, the stronger it is. And of course, the last thing, if you have an order, you can also try to express these rules as ordered rules or sequential association rules. So then you know which product was actually in the basket before the other. And you can even improve this. To improve this analysis, you can add two virtual products in every single transaction. So I will just add product, which I will call begin as the name of the product, and end. And begin will have line item lower than all line items. So the lowest is 1, so I will start with 0. And end will simply have line item number greater than all existing line items. So I must find the biggest existing line item and add a line item with bigger number. Now, when I have these two products, I can also find those products which start shopping sequence. So those products that are always immediately after begin, this is virtual product again. So the product that is immediately after begin is the product that starts purchasing sequence. And the product that is immediately before end is the one that is stopping the sequence. So another way how to find the most positive and the most negative products. But don't forget, you must have an order for this. So let's go and let's expand this query. So again, I will start with combinations of all pairs, express them as rules, count, this is item sets of a single item, right? Count how many times these models are purchased. So I can calculate, I also need the total number of orders, so I can calculate confidence, and I can calculate percentages, relative numbers, right? Simply, I can also calculate the lift with one additional expression. So compared to the previous query, it's just one expression more. So it is probability for the combination divided by multiplication of probabilities for a single model. And now I can order by different measures, order by support, confidence, lift. Let's start by ordering by lift and then confidence. So the most popular item sets will not be on the first place, but those that have really, really strong associations. And we see this extremely high lift, more than 12, for Turing tire and Turing tire tube. Again, yes, this is logical, but you see now it's a different order, ordered by lift. So these two are extremely positively correlated. Also, road 250, HL, road tire are extremely positively correlated. But with the first one, also confidence is extremely high. With the second one, the highest confidence is not that high. So apparently first rule is really extremely strong. And we can go also down since it's ordered by lift. These are negative associations. Lift is lower than 1. So we have long sleeve logo jersey and road 750. These are negatively correlated products, pair of products. And let's say what else? These are really those with extremely low lift, so highly negative associated. You see, patch kit is negatively associated with long sleeve logo jersey, and so on. And finally, let me add the order. Let me add the order or sequence. All I have to do is change the first condition in the first query. So I'm still searching for all pairs. So model from left is different, not lower or greater than model from right. But I added another condition. Line number from left must be lower than line number from right. So I'm adding sequence. So now I will get one item set only once, but not selected by confidence, but selected by sequence. So mountain tire tube is before sport 100. You see the absolute support also goes down because I'm searching only for those where one is always lower on those purchased earlier than another. Mountain bottle cage was most of the time purchased before water bottle, another logical. This one is less logical, water bottle, and then Sport 100. And we have another way how to look at this, to these articles, products. So let's search for minimal and maximal line number. So minimal is 1, maximal is 8. We have, if you remember, we have 13,000 orders. This is just to check the number of rows. So I will add 13,000 begins and 13,000 ends to all of these line items. So to every single line item, I will just add line item 0, which will be begin, and line item 9, which will be end. And this will be 26,000 of rows. Now let's see these line items again. So I have now in the first order, I have 5 products, also begin and end. And now I will calculate sequential association rules, just this time also with begin end. And I will search for products that are very, very frequently associated. Of course, the most important is this one, begin end. Yes, every single order has both begin and end, and begin is before end. Okay, yes. But this one is already interesting. Sport 100 is many times ending. Also beginning, but look at the confidence. Support is the same, right? But look at the confidence. The confidence for the end is much, much higher. So apparently Sport 100 is another quite negative product. Remember, it was the single most purchased product, but now we learned that this is also a product that typically ends the sequence. Also, water bottle in this case is more like negative. It ends the sequence more times than it begins. So it's also interesting to realize these numbers. And this is basically what you can do. Of course, maybe there are some other ways how you can combine these numbers, but these are the most important terms that you can calculate from this item set. So we calculated item sets, confidence, lift, order, and even these starting and ending items. And with all of this information, including these negative associations, you can get some idea which rules are more important and which rules are less important. So let's see how this works in other languages. So in R, we have nice library A rules, and I will just read the same data from my line items. And this is the same data, so I have order number and I have model. Okay, and I could even do this in Azure ML, but I will not do it at this moment. Now I will have to define what is a transaction. So order number defines my 13,000 transactions. It actually creates kind of big matrix. So maximally we have 37 items in a single transaction. And these are, for example, transactions from 6 to 8. So for this transaction is consists of 2 items, and this one of 3 items, and so on. This is just sequential number, right? We can calculate the size. So 2, 3, 3 are the sizes. Now I can use a priori function, feed it with these transactions and with some other hyperparameters. So I'm searching for item sets with 2 items at least, not with single. Support greater than 0.03, confidence greater than 0.05, and I want to express them as rules, not as item set. And I will also inspect them to see the most important rules. So here we have some of the most important rules. So left-hand side, right-hand side, and of course we have these very known products, same results as from T-SQL. For example, this one, Touring tire tube, has really great lift. We have support, we have confidence, and we have lift and support as an absolute number. So now I can calculate, I can use a CLAD function to select the most important item sets, 40, so we can inspect what are these most important item sets of 2, which are the most important from support. It is not sorted, but I can also sort it. Like, for example, these are top N single items. We already know Sport 100 is the most popular, water bottle, the second, and so on. Let's sort rules by confidence. Now, remember, I'm working with matrices here, so physically they are ordered. I don't use an order by expression, but I have to resort them. So this is resorted by confidence, and we have this road bottle cage, then water bottle. Remember, this extremely high confidence, 0.89, nearly 19%. Or by lift, another sort. And yes, we know these two are the most important, touring tire and touring tire tube combination as the biggest lift. Now there is another nice package, A-Rule Swiss, which helps us visualizing these rules. So it overloads the plot. I really like this plot. This plot is extremely informative. So size of these bubbles is defined by the support, and color, the darker, the biggest lift is. And we immediately see this nice combination, touring tire, tube touring tire. Yes, this is the one with the strongest lift, but not really important because they are somehow isolated from all other item sets. Here we can see that on the other hand, Sport 100 is combined with many other item sets, right? Many other. So this is, yes, definitely the most important product. Of course, water bottle is as well. But look at this one, Mountain 200. This is something that is hard to interpret through numbers, but it's easy to interpret through graphs. What is special about this product? Special is that once you come, let's say from Sport 100, you come to this product, Mountain 200, then you immediately go to more groups. So it's more kind of transitional product. So although maybe support for this product is not extremely high, it means it typically leads to another sequence of shopping sequence, one or more than one product. So these transitional products are also extremely important. So something that we couldn't do with T-SQL, since we don't have graphing capabilities here, was very nice in R. Also, I can then do some additional filtering. So, for example, which products are leading to Sport 100? So find the rules, most important. So road tire, tube, Mountain 200. These are those that lead to Sport 100. Of course, this is possible because I have calculated also this confidence and leap. Let's check the opposite. So which rules, which products were purchased most frequently after Sport 100, and we see Sport 100 typically led to these products. Now, all together with T-SQL and with R, we got all of the information. Of course, I get everything I need also from R. I got confidence lift. So basically, I wouldn't even need T-SQL, but it was nice to develop this step by step with T-SQL, which wouldn't be possible with R. But what we got with R was also this nice graph that gave us an additional piece of information. by the way, what would be the usage when you would use Transact SQL compared to R? Well, as you can see, I worked with a matrix in R, in-memory matrix, kind of sparse matrix, where every column, where every item in an item set added me a new column. So we had a sparse matrix, 13,000 rows for orders, 37 for items. So you can imagine that when I run out of memory, this can become, by paging to disk, extremely slow. And yes, definitely, the more data you have, the faster SQL Server will be. Also, in general, in relational database management systems, relational tables, working with them is much faster when you have a lot of data than working with matrices in R or with data frames. Of course, data frames are something between matrix and the table. You can have different data types in different columns, but still order is preserved. Anyway, when you have huge amounts of data, Transact SQL is the right way to go. Now, still R has built-in matrix operations. So let's ask ourselves, what about Python? So what about Python? Well, if you go to data science with Python, then first thing you need to use is NumPy and Pandas libraries. Without NumPy, Python doesn't have built-in matrix operations. So operators, basic operators like plus, minus, are not overloaded. You cannot use plus to make a sum of two matrices. How can you then express this sum? Well, you have to use loops, right? And this is now 100 times, if not more, or 1,000 times slower than using matrix operations. And in general, Python libraries like scikit-learn, you have many algorithms, but interesting is that association rules are not supported by matrix operations. This library for association rules in Python is called a priori, and this one doesn't use data frames. So NumPy is bringing matrix operations, and data frame is brought by the Pandas library, and I'm not using them. So I will just define transactions as a set of 10, 11 rows, very few, right? Because this in Python is extremely slow. So basically, I would say it is simply useless. Now it works fast, but I have 10 transactions. And now I created rules as a list, and now I will extract these rules. You also see that this is not a simple thing. And I have this, so rules left hand side, right hand side, support, confidence, lift. Please note that these are completely different numbers. I'm using really a small subset of data. Let me show you what is the difference of having matrix operations or not. So I will just compute reciprocal values of some numbers. I am defining my own function, and I will calculate the size of this is 1 million, right? So I will calculate reciprocals of random integers between 1 and 100, 1 million, right? And this is okay, already was calculated, but I will now also measure the time. Now I will also measure the time and start the time, print them and end timer, and measure the time in seconds. And you see, it took me 2.6 seconds to calculate this row by row, right? Now, because I imported NumPy, the divide operator is already overloaded with matrix operations. So let's calculate it with vectorized version. and it was 0.1. So it was, you see, how many times? 260, nearly 300 times faster. So basically, it means that these association rules in Python are more or less useless. Now comparing this performance, we got like 300 times difference between loops and matrix operations. But if you go to relational side, you can even get another 100 times faster with really huge data sets. So also having this algorithm developed in Transact SQL could be extremely useful. Now I will just show these association rules in analysis services. They are very, very nice because they have some really, really good viewers. This first viewer is showing us rules sorted by confidence, and then importance is lift, right? And you can also filter the rules. And it has also this dependency network similar to R. I will just show attribute name, where we can easily see those transitional, like patch kit is one transitional, sport 100. Basically, you probably know that in SQL 2022, data mining is already discontinued, so it will not be even included in analysis services multidimensional. I'm really sorry for this because it still has its place. It's very simple to use and it has great visualizations. I at least hope that they will not lose these visualizations, that they will not disappear. For example, if you go to Power BI, we have this is an additional downloaded association rules visualization, which is pretty impressive, but still not so nice, right? And let's go to visualization. I can change the visualization to graph, let's say, and you see it is working. It is. I have only subset of rules. It is slow, much slower than Transact SQL of R or R. Also, visualizations are very basic. I really hope Microsoft will not simply forget on this analysis services visualization. Of course, numbers are different because I extracted only subset of data for the performance. So it has very, very basic usage. Anyway, to somehow conclude this, so you saw how I developed this step-by-step in Transact SQL. And out of these solutions I have shown, the Transact SQL is great one with numbers, but also R adds this nice graphical presentation of rules, which is important. Python is more or less useless unless there will somebody find another more efficient library for association rules. Power BI with custom visualization, yes, somehow partially useful still for small data sets. Also, this custom visualization is based on R. If I go to R code, it is using, no, it's not this one. It's using some other visualization for clusters, is using dbscan library. So altogether, Transact SQL or R, this or both, these are really useful. Analysis services was extremely useful. Data mining for association rules. Unfortunately, Microsoft is simply discontinuing it. I'm a little bit disappointed. I mean, it still has some room, because not everybody wants to learn programming in depth. Maybe you have a smaller company that just wants to check some simple data science things like association rules, and they don't want to hire a data scientist or developer that would know all details of Transact SQL or all details of R or start learning the new language. and still you have great visualizations that help you with understanding. As I said, I only hope that these visualizations won't be lost. Okay, so since we are in this small group, I am in the end, so at least you can catch the schedule now. Any questions, any comments?